Welcome to a new test and teardown video. This time it's a Fluke 1941A Digital Counter. I believe this one is from 1974. Oh, and it will go all the way to megahertz. And I don't know how many digits it's covering in megahertz, so I can't really tell you yet. But of course we're going to figure that out real soon. I was googling a little bit around to find some more information about this unit, and I find a guy called Jason who took a defect one and turned it into a clock. It's because this one got 6 digits, and it's real easy to imagine this one as a clock because of the size. It's actually quite compact and really nice for a 1974 device. I think it's really nice and compact. I cleaned it up using hot water and thinned alcohol because you cannot use pure alcohol on this type of paint they used. So you need to be careful on that. Switches appear to be good quality. So yeah, I just feel like just powering it up. Before we power up, of course, I inspected voltage selection is correct. Clock input is 10 megahertz. And for 1974, also look at the IEC connector. They are definitely ahead of their time. We got BCD output, BCD preset, and we got some upgrade options available. I kind of like that. So let's try and power this up. I got 230 volts connected to it like that. And it is 20 watts. It is very bright. And by the way, of course it says 40 megahertz here on the front. This is not the same as this is its actual maximum, or is it the guaranteed minimum? Let's try and give it some input. Poof, that is 1 kilohertz. Let's go to kilohertz. Hey. And how about if I go here? Oh, this is 1 times per second, right? So this is 1 second, it says here, right? So this is, it's gating 1. So the resolution is ±1. It can even go 0.6. That is funny. Ah, this is because then it's rotations per minute. How cute is that? I love it. I think this is one of the first time I see this feature. And if I go here, yes, of course it's total and then reset. Wow. I like it so far. Okay, so I just tried a little bit to play around with this unit here, and we're now in kilohertz. Well, my input is 1 megahertz. But that is 1 megahertz, and it's look at that. It's jumping a lot. So it's not doing so good at 1 megahertz. Let's go to a 100 kilohertz. Aha! Nice and stable. So that is 100 kilohertz, and then this is exactly how nice and stable it should be, right? So if I go to 500, okay, so that's also okay. 6, 7. And then it starts getting jumpy. 900, and that is 1 megahertz, and then it gets really crazy here. So there's definitely something going on in this counter that is not supposed to be like that. So this is 1 megahertz. Let's go to, okay, let's just go to 10. See what I'm saying? This should be 10 and it's way too little, right? And this is 20, 30, 40. No luck at all. Okay, let's open and see what's wrong. What exactly is that? Can you see this shiny goop? And it's also, ugh. And of course I tried to touch it and it was like slime. That can't be good. So here is this nice unit inside. And the 6 tubes. Haha. ZM1000. I kind of had that idea when I looked inside, or when I looked, you know, from the front. So yeah, the classic ZM1000. Those are really, really beautiful Nixies. So I'm a little bit more inside this unit here. I desoldered the wires up here for the overflow LED. You can definitely see on the Nixies now, they're not brand new anymore, but they're still really nice and bright. And that could have something to do with the anode resistor values they have picked, and also the anode voltage they are running at here. So this is something I want to look a little bit at. They say 170 is written here on the PCB, so I will double check that. I also get a little bit scared when I see tantalum capacitors like that. And that is the decoupling capacitor for this entire counter circuit. So you see, I think that will be the counters, right? So those are counters 74196. So all this, and it's just this one capacitor, right? Also, if you see the layout, this is clearly done manually. And then, oh, we need to do that. And what was the idea? Oh, then we just do it like that. And so you see different ideas when there is progress on the layout. And here's definitely some high voltage, high power stuff. Those two resistors, they get very warm. I can even see the soldering is like cracked and looking really bad. So when you got really, really warm resistors like that, you can even see how dark it is here. And then there's a capacitor right next to that. And it says 400 volts, this capacitor here. So I bet there's nothing left in that one. And again, very few decoupling capacitors. I just hate tantalum capacitors, but that is a whole different story. So the input goes to a little amplifier, and then I bet that one is a pre-scaler, and maybe we can check it out. It's called MC10L. What is that? Hang on a second. Let me do it a little bit better. I'm sorry. Okay, here we go. 10116L. So isn't that a pre-scaler or an amplifier or some stuff? And then we got some gates and a counter. Okay. I bet if I take my scope on some of these signals, I will be able to see what is going on and what is not going on. I also see some really nasty repair job down here. What is that? Oops, acid damage or some. What is that? Oh yeah. Here is another little thing to service. This is 30 megahertz. This is just so typical what happens when I poke this to pieces and start investigating on the problem, then it's just gone. I think it's maybe also because when I took everything apart here, I took my paintbrush and then I carefully cleaned everything from dust and stuff. And maybe some of this dust was a little bit electrical conductive, or it was creating some sort of a, I don't know, a leak. Because that is 30 megahertz and it is nice and stable. That is exactly what I want to see. And if I give it 40 megahertz, oh, this wire is a little bit annoying, sorry about that. Okay, here we go. Let's try the 35 is still quite alright. 38 is okay. 39. And then 40 it starts jittering, and maybe that has something to do with the input level. So I just give it one extra. 2, 3. No, it is not a sensitivity thing, but I have just reached this product's maximum. So the 40 here is on a very good day or when it was new. So that means 39, bingo bongo, accurate. And 38 is even better, right? Okay, great. Happy. You gotta see this. Now okay, let's try this again. 30, 40, then it is exactly at 40. It's crazy. But how about 50? What? How is that possible? How is it able to do a lot more than it's actually specified to do? So that was 50. So let's try 60. Let's try 70, 80, 90, 100. Okay, so that is 50. It works perfectly fine at 50. So how about again? I think what happens here is now I connect the prescaler, right? So that is 50. Then it goes 60. Yeah, 70, 80. Okay. So now it's doing 70. Yeah, it's the same. Yeah, okay. So I can't explain this 40 megahertz kind of unstable, funky behavior here. Maybe this filter is, that is working. Definitely see there's a 1 megahertz filter. So how about we give it 1 megahertz? 1 megahertz work. 2, 3, 4, 5, 6, 7, 8 megahertz. Of course it has something to do with sensitivity. So if I crank down the input to like 500 millivolts and then I go back to 1 megahertz, then it works, right? And then 2 megahertz is not working. Definitely. So that is good if there's noise on your signal and you are going on slower signals. So I've been playing a little bit with fine adjustment of the frequency, and I've also played a little bit with the high voltage. Is indeed a little bit in the high range, I would say. So also I tried to play with the input voltage. Look at the brightness here. This is all the way down to where it starts to crap around right here. So this is 186 volts, and if I go from this point and up, see what happens with the brightness. So, and this is all the way up here to 230, where it's way too bright. See? So anode voltage is of course not regulated in any way. Here we go. So that is all I wanted to show you guys. I hope you had fun. Please come again tomorrow.